Welcome, everybody. If anybody else joins, then I'll just admit them in a little bit late. But I want to go ahead and introduce our speaker for our seminar series with the Center for STEM Education. So our speaker today is Dr. Janet Walkoe. Janet is an associate professor in the Center for Mathematics Education at the University of Maryland. She earned her doctorate from Northwestern University in the Learning Sciences in 2013. She also holds an MS in mathematics from the University of Illinois in Chicago and a BA in mathematics from the University of Chicago. Before enrolling in graduate school, Janet taught secondary mathematics for 10 years and earned National Board certification in 2003. Janet's research focuses on the teaching and learning of algebra. Having been a former secondary teacher, she is aware of the status algebra holds and the important role that it plays in children's access to higher education and the workforce. Janet's research interests include ways to help teachers attend to and build upon children's algebraic reasoning. In particular, she's interested in how teachers attend to and make sense of multimodal student thinking and other student resources, including but not limited to student dispositions and students' ways of communicating mathematics. Janet's work has been funded by the National Science Foundation, the Spencer Foundation, and the U.S. Department of Education. Her work appears in journals such as the Journal of Mathematics Teacher Education, Mathematics Teacher, and the Journal of the Learning Sciences, among others. So, Dr. Walkoe, welcome to our series.
Thank you.
I'll turn it over to you.
Thank you so much. And thanks so much for inviting me. I'm so excited to come and get to know the community a little bit better. I'm also admitting people at the same time. I'll stop admitting now and focus on the screens. So thank you, Allison. As Allison mentioned, I'm interested in how to help teachers attend and respond to student mathematical thinking. And so that's what I'll talk about today. Learning, and feel free, by the way, to stop me at any point if you have questions. It's kind of, I like the dialogue aspect, and there will also be time for questions at the end. So learning to attend to student thinking is something we all try to do, but actually does take some practice to learn. We need practice understanding and learning what to see, and it doesn't come, some of it comes naturally, some of it doesn't. So that's what I'm here to talk about. But before I get started, oops, let's see, make sure. Oops. Okay. Before I get started in the content, I wanted to just tell you a little bit more about my teaching experiences. I was a secondary teacher for about 10 years, 5 of them in Chicago and then 5 around the East Coast. And I was National Board certified in 2003, which now is 20 years ago. Hard to believe. That was that long ago. I've had experience mentoring teachers as well, both in summer courses and where they were doing their student teaching in summer courses, and also supervising teachers in the classroom. And then in addition to that, I do research on teacher learning. And I wanted to share some of my commitments as a teacher educator. I'm interested in helping teachers develop and lead conceptually rich mathematics tasks for all students. And part of the work of this includes teachers' views of student resources, which I'll talk about in a little bit, teachers giving students opportunities to share their thinking and to think about math, and also how teachers position students. And so all 3 of these things are important in helping students have access to these rich mathematical tasks. So not too long ago, well, not longer ago, but in the late 1990s, early 2000s, the field started thinking more about teaching practices and the work of teachers. And so the shift was from teacher knowledge, what do teachers need to know? So what do teachers need to be able to do? So they're both things are a part of this. Core teaching practices is one way that the field talks about this. These are practices specifically that occur often in teaching, practices that can be studied and practiced and examined. These practices allow novice teachers to learn more about teaching. They're research-based, so what practices are effective in the classroom, and they also preserve the integrity of teaching. You also may have heard about the high leverage teaching practices. This is more of a concrete list of discipline neutral, so there aren't content attached to these specifically, but different discipline neutral best bets for teaching. So what can teachers do to improve their practice, and what kinds of things do teachers need to be able to do? And I talk about these because this is where research and practice align. And my work specifically addresses the third high leverage practice, eliciting and interpreting individual students' thinking. So that's where a lot of my work it can be found, and where I connect research and practice. So going back to the core practices, I want to distinguish between demonstrating a skill, being able to check it off on a box, versus flexibly engaging in practices. So when I think about eliciting and responding to student thinking, I like to help teachers do this flexibly. So it might be something they're not prepared for. And how do teachers negotiate that? How do they learn to pivot and attend to student thinking if an unexpected answer, for instance, comes up? The theoretical lens I take on this is one that we call teacher noticing. And it has three key components. Identifying, or three that we focus on, or that I focus on in my work. Identifying significant moments of instruction. There are literally hundreds of moments a teacher could attend to in the classroom. So which one does she identify as important? How the teacher interprets those moments, and then how the teacher decides to respond to those moments. It might be asking a question. It might even be looking to another student response. For instance, it might be ignoring that moment. So a teacher notices something and then has to make decisions about what they do with that moment. And so again, returning to these commitments, I'm going to focus on one in particular today, and that's views of student resources. So I'm going to get a little bit kind of theoretical here, and I'm going to hopefully ground that in practice, and feel free to stop me and ask questions if this gets a little confusing. But my view of student resources is that students, I think it's on the next slide. Yeah. So a resources-based theory of learning. Student thinking is complex, and we don't have either fully right or fully wrong ways of thinking, but they come to the classroom with deep knowledge from living in the world and resources they can use when learning about math and science. I throw science in here because I also teach some science methods courses, math and science methods. And students can use this knowledge in more or less coherent ways. So what a student says usually makes sense to them, even though it might not make sense to you. So understanding what they're thinking and why this is making sense to them is part of the work of a teacher. And student thinking is dynamic. So students use their knowledge flexibly, and oftentimes they construct their thinking on the explanations on the fly. So when you ask a student a question, usually they haven't thought about and developed an answer before they start to talk. So they're thinking as they're talking many times in the classroom. And the professional development that I focus my work on most to help teachers attend and respond to student thinking are video clubs. And here you can see three little clips, or three little photos from a video club that I had led over the years. And you can see first, the teachers discuss the math. That's the picture you can see on the upper left-hand corner. They're discussing the math that they'll see students thinking about in the video. Then the teachers watch the video. It's usually a 4 to 7 minute clip. It's not too long, so the teachers can notice moments and then talk about them later. And then the third part is teachers discussing the student thinking that they saw in the video. Often, and we'll do a little video club in a moment. Often I ask teachers what interesting student thinking they notice. And then we kind of it's a very general prompt, but then we kind of have discussions about that in the video club. And they can think about what student thinking they saw and have discussions about it. So we often compare it to a book club, except teachers are discussing this video clip. Okay, so here I'm going to give you did I miss? Let's see. Oh yeah, here it is. So here we're going to do that first part, doing the math. We're going to all think about this problem before we watch a student thinking about the problem. And this is a little different from a classroom clip because this is when I was a graduate student, actually, so many years ago. It shows me interviewing a student about this question and trying to understand how she's thinking about it. So I'd like to take a moment for everybody to read the question, think about the answer, and then maybe some brave volunteers will, brave people will volunteer their answers and the way they're thinking about this. So go ahead, just take a couple minutes. I'll start my timer. 2 minutes to think about this problem. Okay, about 30 more seconds. Okay, so I'd love to hear how people thought about this question. Any volunteers? Oh yeah, Caroline,
So, can you hear me okay?
I can.
Okay. So I converted them to decimals and that I compared the decimal size to determine which one was more lemony.
Excellent.
So,
Yep.
okay,
So
yeah,
which you,
and 0.25 compared to, or 0.75 compared to 0.667, I believe.
And so whose was it, Maria's or Janelle's, who the 3 to 4 or 2 to 3 that was more lemon, could have tasted more lemony?
That would have been, oh my gosh. Oh my gosh, I hope this is right.
It's your answer's right.
Janelle,
Yes,
right?
yes, yes, exactly. Excellent. Thank you, Caroline. Appreciate it. Any other ways of thinking about this? Yeah, Samantha.
Hi. So I was just doing it by hand. So I found a common denominator and worked it out as a fraction. So Janelle's was 15/35, and Maria's was 14/35. So Janelle's was lemonier.
Okay, super. Thank you. So you got the same answer, did it a slightly different way. And you had the denominator was 35. And
Yes.
so, yes, okay. So I want to just see if anyone, so you two both got the answer right. You did something slightly different. Does anyone notice what was different about those two? They were different fractions / decimals. What do you think? How are those different? Does anyone notice? Did anyone notice? I wish I had a whiteboard here. This is the one thing about Zoom. I think there is one, but I'm not going to try to do it because I think everything else will then stop working.
Are the fractions, for me, it was like a visibility thing. Like whenever I was picturing them poured out, you could, in my head, I can see the difference, but working out as a fraction made it more visible in my mind.
So you like to see it as a fraction rather than converted to a decimal?
If I'm doing it by hand, I do.
Yeah, Yeah.
And I'd never take the fraction route.
Yeah, we all have these ideas of these some maybe potentially bad memories of fractions. So one thing I would love to point out, I love that both of you thought about it differently, both in terms of fractions and decimals, but also I think Caroline, I think your decimal was 2/3 and 3/4. And then Samantha, I think that your fraction was 2/5 and 3/7. So there was a slight difference in how those two were thinking about the fractions even before it came to decimal phase or decimal state. And so I think, Caroline, you were thinking about the 2 lemon to 3 water. And then Samantha, you were thinking about the 2 lemon to total mixture. Yeah. So you'll see these answers along with many other answers when students think about these problems. Thank you both for volunteering. I appreciate it. I know, especially on Zoom where you pop on, it's a slightly more different thing than sitting in a classroom. But yes, great ways of thinking about this problem. And I want you to take I'm not going to give you too much time now, but a couple moments to think about how a 7th grader might think about this problem. Just going to give you about 15 seconds. What of those 2 ways or other ways might a 7th grader use? You don't have to answer, just want you to start to think about it. Put yourself in a teacher's shoes who might be teaching it. Okay, so we're going to do a little video club type thing. Now, I don't expect everyone to, turn on videos and do a lot of talking, but I'll show you what we might experience if we were doing a video club. I would have the teachers work on the problem as you did, and then I'd show them a little video clip, which you're about to see. And as you watch this clip, I want you to think about a couple questions. First of all, what interesting student thinking do you notice? So what do you notice about this, what the student's doing? What do you think the student understands? And what might you want to ask the student? So to kind of break those down, because I'm not visually showing you those questions, what's the student, like what do you notice is interesting in the video, and what might you want to ask the student to help further their understanding about that same problem? Okay, so she just did the same problem, and then here I am interviewing her and asking her about it. And this clip is only a couple minutes. Let me know if you cannot hear the sound. I'm hoping the sound plays.
Should I?
Oops, sorry. Ooh, I guess I have to show you in this.
Whose lemonade tastes more lemony, or do you think they taste the same?
Should I work it out?
Whatever helps you think. Yeah, whatever. However you want to think about it.
I think they'd be the same because it's equal proportions or portions. I don't know what the word is, but
Okay. What do you mean by they're equal proportions? Or equal portions.
like there's 2 cups of lemonade or lemon juice.
Lemon juice.
And then for Maria, and then for Janelle, there's 3 cups of lemon juice.
Okay.
And then they each she used 3 cups of water and she used 4.
Okay.
So that's like kind of the same because the numbers just increased by 1.
Okay.
So she would have more lemon juice, but they would taste the same. Or she would have more lemonade,
Okay.
but they would taste the same.
Okay. Which numbers increased by 1? Which numbers were you talking about?
Well, the 2 goes to 3 and the 3
Okay.
goes to 4.
Okay. So to get from Maria's mixture to Janelle's mixture,
Yeah,
each thing goes up by 1. Okay.
yeah.
let's
And
see.
then they're each one apart. Like it's not like
Okay.
3 and then 5 and that's 3 and 2 because then this would be more lemony.
Okay, so let's see. So what's going on here? What did you notice about the student thinking? And let's just start with that. What do you notice about this student thinking? Is it correct? Is it incorrect? What's she doing?
She was thinking more logical than she was thinking math. She was just thinking about like logical stuff instead of like doing the math, you know.
Yeah, yeah. So kind of explaining it, but she wasn't working anything out, so to speak. Any other noticings or comments?
She used the correct vocabulary, like proportions, but
Mm.
then it kind of seemed that she didn't get necessarily the concept of proportions.
Mm-hmm. Yeah, yeah. Oh, I see a chat. I didn't open the chats yet. Oops, move this over. Yeah, part to part, part to whole. Exactly. So Julie said part to part and part to whole. So you can look at, does everyone, I'm just gonna, so you can look at the lemon to the lemon, or you can look at the lemon. Oh, so Julie, this was from before. Oh no, yeah, you can look, sorry, you can look at the lemon to the water, or you can look at the lemon to the whole mixture, part to part to whole. Those are definitely things that are coming up here. So is there anything, what would you want to ask the student? Are there any questions you might want to ask her to follow up on this?
I'd want to know how many cups of lemonade are each girl making?
Mm.
Because I think if we kind of move in that direction, sort of, that might help to think about the part to the whole. And then the real question is, how lemony is it? Right.
Yeah. Yeah. So giving her little hints like that to kind of think about things in a different way than she is, looking at the whole mixture rather than just the parts that she's looking at. Anything else? So usually I give a little more wait time, but I'm noticing the time here, so I'm just going to go forward because we are going to do another exercise. So this was what we discussed. What interesting student thinking did you notice? What does she understand? And so I hear she understands vocabulary, some of the vocabulary too. She certainly heard these things in math class. This kind of brings her back to math class. And then, so she understands that the idea of proportions, or that proportions are a thing. And then you might want to ask her to kind of broaden and look at the whole mixture. Great. So we're going to take a deeper dive now. Same student, moments later. Okay, this might surprise you. Same student, moments later. So here, I asked her if she wanted to use some blocks. She could use yellow blocks for lemon, white blocks for water. And I asked her if she could show me with blocks, a mixture that tasted equally lemony to Maria's, the 2 to 3. So she made Maria's mixture, and then she did something that was a little surprising. She scaled up. She made Maria's was 2 to 3. This is 6 to 9, same proportion. And she just did that. For here I was thinking, oh, maybe she's using additive reasoning, adding one to each instead of multiplying each by a number. It's multiplicative. But then here she does it. So this one actually is would be the same lemony. It's a bigger amount of lemonade. So that's a little surprising to me. And then I asked her to make another one, and she did all 3 of these. Or sorry, this one, 4 to 6. So she started with 2 to 3, scaled up 6 to 9, and then scaled in between, but scaled again 4 to 6. So she was easily able to pull these out to make these block models. And so that was kind of interesting. She knew more about proportional reasoning than I had first thought. And so now here is the second part of the video. Again, it's going to show the video lines. Okay, so let's watch this and now see what we think she understands about the problem.
So Janelle, can you make Janelle's mixture using blocks?
Sure.
Oh, let's leave these.
Oh,
Sorry.
okay.
I just want to think about
That's
all
okay.
this together. Okay. Yeah, so let's look at Janelle's mixture.
So this is the 3 to 4 I'm asking her to look at now.
The yellow cubes is 1 cup of lemon juice. Yeah, for her original mixture. Yeah, I'll just use this as next one. Okay, and so originally, this was Maria's, and this was Janelle's mixture.
Yeah.
Okay, and originally, you thought that they tasted the same.
Yeah.
Okay. So all four of these taste. Would you say that all four of these taste the same?
Yes.
Okay. Okay. And tell me again why these three tasted the same, the ones that you made.
Because I just multiplied the lemon juice by a number to get these numbers, and then I multiplied the water by the same number to get the amount of water.
Okay, and then why, again, were these two the same?
Because there's one less lemon than there is water
Okay, for each of them.
for each of them.
Okay. Okay. So, let's think about, let's see, let's think about,
I'm just going to stop it right here because I want to ask you. So, do you see what she's doing? She created these that are the same as the 2 to 3. She's created the, she said she multiplied the lemon and the water by the same number. And then she still thought that the Maria's and Janelle's tasted the same lemonade. The 2 to 3 and the 3 to 4 were the same. But she used different reasoning. She said, because there's one more water than lemon in each of these. As teachers, as teacher educators, teachers, mathematicians, what might you ask her next? Do you think so she thinks these two things. What might you ask her next?
Might ask her to compare, like, do the 3 that she originally made match with the new one,
Mm-hmm. Mm-hmm.
and maybe come at from a matching standpoint.
Mm-hmm. Yeah, yeah. So she had the 2 to 3 and easily scaled up. But what happens when she compares those easily scaled up ones to that 3 to 4? Interesting. Yeah.
I think I would ask her if the first 3 all taste the same, like they're all the same amount of lemony, and you're using, that the additive thinking for that first one, would that one still taste the same as any of the other 3 or the other 2 that you had made?
Mm-hmm. Mm-hmm. So doing that, yeah, I like that. Just kind of having her cross the way she even has it laid out. It's like she's comparing these and then she's comparing those. But like, what if you're asking, and the two of you are thinking, like, what if you're asking her to do things that are a little more, you skip around a little bit, because the way she has it laid out, it's kind of easy for her to still think that same way. Compare these 2 and then compare these 4 or 3. Hey, any other thoughts before I show you the rest of what I actually asked her, the rest of the video? And I'm not saying that what I actually asked her was the right thing. It's just the way that the video unfolded. Okay, so we don't get to the very end, but let's see what she does next.
these, let me take this down here. So, can you make another one that would taste the same as this?
Yeah.
Using the blocks. Or maybe you'd want to use one that's already there.
Actually, yes.
So Allison and Samantha here, she's kind of doing the thing that you were both thinking about. She started to do it.
Okay, so is this done?
Yeah.
Okay, so these 2 taste the same?
Yeah.
All right, so then would all 5 of these taste the same? Equally lemony?
Theoretically.
Okay, what do you mean theoretically?
Like, well, in mathematical terms, yes, but like, I don't know,
But what do you-
lemonade is different, I guess. It could change.
Okay, so you're talking about
Okay, so that's the second video. Comments. Does she understand proportional reasoning? There's something you might ask her next.
I'm not sure if she is still, it's like she's trying to make what she already thought fit. And it doesn't.
Yeah. Yeah. Yeah, exactly. Let's spend another minute or two on these questions. So does she know more? Does it seem like she knows more in this second clip than you might have thought she knew in the first one?
I think so, because she knows how to multiply at least properly, right? She knows how to increase the amount of lemonade. But then her comment about the lemonade at the end is also kind of interesting because now the context is sort of confusing her. She's like, well, what kind of lemonade? And so I think, the application might be compounding her confusion at that point.
Yeah, exactly. And I love that. Well, if lemonade is whatever, whatever she says at the end, kind of like it might not. I don't know if she meant it might not follow the rules of math, or the context kind of seems different to her. But and also the funny thing about this problem is if you really tasted those mixtures, they probably would both just taste bad because there's no sugar. They also might taste equally lemony, right? Because I mean,
Yeah, we can't differentiate that closely, right?
Exactly. So, okay, so the main point with these videos is to just kind of demonstrate this. This is an analogy I love using for student thinking. There's this iceberg, there's the tip of the iceberg that we can see, asking some basic questions. And as a teacher, a lot of times the tip of the iceberg is all we get to see because we have 30, maybe more students, and we ask a question and we hear little bits here and there. Some students we don't hear from, we just see maybe their work on paper. So the tip of the iceberg is what's often visible to teachers, but there's so much more. And so this eliciting and responding to student thinking is one way to help us kind of delve deeper. So if you hear something that you might be confused about, or that sounds like maybe it's on the right track, or you want to know more, I often tell my students that it's almost like excavating, kind of digging and unfolding the layers and seeing what else is there, because there's so much student thinking we can't see. So for teachers, it's really nice to be able, or it's important to be able to dig deeper. And sorry, it made some little, so that's kind of what we see, but then there's all this thinking that we don't see. So that's, in my methods course, that's what I talk about a lot, is how important it is to, instead of lecturing, I mean, there are times we need to lecture, and I'm not, of course, not against that, but there are also times when you want to know what students are thinking, and that's where formative assessment comes in, and kind of delving more, maybe sitting with a group as students are doing group work and asking questions. I'd love to know, just a couple minutes, how you all, either in your own teaching practice or when you're working with pre-service teachers, how do you help them, or how do you dig deeper in the class to student thinking? How might you uncover some of that underwater parts of the iceberg?
So I'm not math, but in science we have a lot of the same issues. And so with my pre-service teachers, I really put forth hands-on investigations. They have to solve a problem just like I would if I were in an actual classroom, and I let them experience from the student standpoint. And there are a lot of misconceptions that bubble up and a lot of discoveries. So having that opportunity for them to investigate a problem on their own helps us dig down. And so then when those misconceptions pop up, then we can address those almost as a class sometimes. And it's like, well, why did we think that? And what made you think that? And what were maybe some previous teachings that led you there?
Great. I love that. I love this idea of using like confusions or things that come up or things that aren't correct as places to really dig in and delve deeper.
So I have a daughter, she's in the 4th grade, and she has math questions that say, explain your reasoning, and they drive her insane because she's like, it's 5 plus 5, like that's obviously 10. Like, I don't know how to explain that. But I think questions like that would help them understand like how they came to that conclusion in more complicated problems like this.
Yeah. Yes. So as we know, both as educators and possibly having children in education, my daughter's 13, she's in middle school right now. Yeah, I think sometimes if children are asked to explain reasoning, there's sometimes where what else is there to say? But then there are other places those prompts can really be useful. And sometimes it even takes more of a just some kind of follow-up prompt. And especially with problems that are a little more complicated. 5 plus 5, yeah, it's a little harder one to, unless they've been working on some specific method. But yeah, and I think that schools are leaning a lot more toward that now with evidence and ways they do assessment, which is great. I think that's a really good shift in schools. So speaking of shifts, I'm going to shift gears a little bit and go into some kind of a slightly different realm, but it will all tie together in the end. We don't always have the luxury to do, I love in science classes, we get sometimes chances to do labs and do investigations and hands-on things, and that's fantastic. That's ideal. But sometimes we don't have the opportunity to do that. We're teaching something quickly, or we're teaching on something they need to know on to go do this hands-on activity, or they need to know to go on to do these things. So when we don't have the luxury to delve deeper and see that deep ice underneath the water, what else can we do? And this is kind of the newer, some of the newer work that I've been doing. And we're starting to do this with teachers, and that's a whole, I have written some things about this, but that's a whole other talk. But I want to just introduce this idea because I think that it's really helpful to educators, not just delving deep and asking more and more questions, but more with what we see, what can we do? So that's kind of the segue into this new thing. So I've written something recently on what I call seeds of algebraic thinking, but it could be seeds of anything thinking, seeds of geometry, seeds of computational, seeds of scientific. The idea is that I'll describe what these things are. By seed, you can tell they might be small. These are little bits of knowledge. So they're pre-conceptual knowledge pieces. Getting a little theoretical here, I apologize. We'll circle back. That come together to form bigger conceptions. I'll give examples of these in a second. Seeds have long developmental histories, so children pick up these seeds of knowledge from when they're little babies and they carry them through life. Seeds are subconceptual, meaning it's not the earth is round, the earth is flat. They're not full conceptions, they're subconceptional. A seed can show up in many conceptions, and they're contextually activated, not inherently correct or incorrect. So if someone asks me a question, a bunch of seeds will be activated to come together to form this idea. Okay, so those are the 3 big pieces of seeds. Here are some examples of seeds of algebraic thinking. I'll just go through these and tell where these might be found. Replacement. So often my daughter, when she was little, would play school and have a teacher using her stuffed animals. Any of her stuffed animals could be that teacher. That's what I mean by replacement. It's this empty box. Anything could be subbed in or subbed out. She had an idea, so that's kind of like a variable, or this idea of an unknown or a box to be filled in. In betweenness, Goldilocks and the 3 bears, too hot, too cold, just right. Or a child in between 2 adults. This idea of in between, children understand. Balance. I'm on a teeter-totter. I need 2 friends to balance my dad when I'm little. It's this idea of balance. So Same direction change, two things go up together, or two things go down together. Opposite direction change, as one thing goes up, the other one goes down. So kids experience these things in life. Closing in, so you're playing the game hot, cold with your an adult that's with you. You're getting warmer, warmer, cooler, cooler to find something, but you're closing in on it. These are what we call seeds of algebraic thinking. They're things that kids experience and learn by living in the world, but they can come together to be highly algebraic. For each of these, I can think of an algebraic conception that these things are key to developing calculus even. Replacement variable, in between this, intermediate value theorem, or sometimes when you're trying to find a solution to an equation, balance, solving equations, covariation, opposite variation functions, and then closing in, something like limits. Okay, so these are things that come up in math, but they're also all kids know these things. And so here's a quick example of in-betweenness and closing in children's informal life, and then how they become more formal. So the game hot coals. Okay, this is really cold, this is really warm, so and then you're getting cold again, the thing has to be in between these two areas. Closing in, warmer, warmer, cooler, cooler, you're starting to get closer and closer to the target. Same thing when you tune a musical instrument. You have the sharp, a little flat, and then on tune. So you're getting this idea, the thing I'm looking for is in between these bounds, and I'm getting closer and closer to it. So those are in children's informal lives, but here's an example from my colleague's paper where she's having a child do a word problem, middle school kid. Anne is twice as old as Paul. Bill is 5 less than Anne's age. Together, Anne, Bill, and Paul, their ages sum to 147. How old are they each? And so what the kid did here was he tried one guess and found out that was too low. Then he did another guess and found out that was too high. And then he did another guess, and so he thought, okay, this one, and that was just right. So the idea of betweenness and closing in. And you can see in algebra and calculus, limits, theorems, or lots of these seeds come into play. So what does this actually mean? I want to just talk about, we saw this early example where the student said they're the same because each is one more. There's one more cup of water than lemon in each of these mixtures. That's not right, but the reasoning she's using isn't entirely wrong. And so how can teachers recognize these resources? So I did a video club with some pre-service teachers after introducing them to seeds. And one thing they noticed in this video was that each being one more is a very valuable resource in some cases. When you're solving an equation, you add one to both sides and it stays equal. So just kind of recognizing what the student's doing that isn't quite productive in this situation, but is productive reasoning, and we can kind of build on it and use it for something else. So I'm running out of time. I was going to have you watch that first video clip again and think of potential resources, but I think you could do this, in your own, when you're working with children, or see videos of a student learning or student thinking, or even in your own life with your students or your children. Seeing these little algebraic or any mathematical glimmers in things that they're doing that are not formally mathematics, and thinking about how the children have these brilliant resources that they're bringing to class, and we can leverage those in class. I zoomed through the second part. I apologize. It's the newer part of what I'm doing right now, and we're still working through how to use seeds with teachers to help them build on student and help support student learning in algebra in particular. I wanted to show you this. Anotemos is what we've been using in video clubs, which is a fantastic tool. We've written a couple of things about this, but what this allows us to do, and if I'd had more time, we would have each made an account, and you would have tagged moments that you noticed were interesting in the video by pushing a pin right here. And then I could see, and you could see where tags clustered. So maybe a lot of this, each line is another person's tags, and this timeline is where each person tagged. So once they're done, you can see clusters. A lot of people thought this was interesting. A lot of people thought this was interesting. You can delve in and talk about that moment then. I know that you came to hear a talk. You didn't want to be an active doing math necessarily right now. But if we had this tool, I could kind of see what you're tagging, and we could have those conversations. So that's a way to kind of facilitate the video club, see what people are noticing without them having to say something. And just to quickly tie in how I wanted to demonstrate today what I'm committed to as a teacher educator and how the research can help support that. Thank you. That's the end of the formal part. And I'd love to engage more and answer any questions you have. I'm going to stop sharing the screen so I can see all of you. All right. So feel free to write questions in the chat. I have the chat open. I have the grid open so I can see folks. No pressure to turn your screens on. I just want to be able to see if you do. Okay. But yeah, I'd love to take questions.
I have one real quick because I've got to run to class. So
Okay.
I read through one of your papers, and it was on the teacher noticing gestures with their students. And I was wondering if, since we're in, the melting pot and there's all sorts of different ethnicities in a single classroom,
Yes.
does that make a difference in the way that the students will gesture? Like if their culture is not big on gesturing, will they just kind of just sit and stare? Or if their culture is really big on gesturing, do they make movements that you notice, but actually are just how that student behaves?
Yeah, that's a great question. And that's something, Samantha, that's something that we haven't looked at right now. And anecdotally, I think maybe, gosh, I think a lot of you could speak to this as much as I could. I know that I have at least friends who gesture more and gesture less. I'm thinking about cultural groups. And I don't know that I have enough data to say for sure that they gesture differently. I'm sure there are differences, and I'm sure there are different norms too. So that's a great question, and it's something definitely worth looking at. One thing we are looking at is we're doing math thinking interviews with bilingual students in Spanish and English, and we're looking at how they use translanguaging, so meaning body movements, gestures, switching between two languages to express their mathematical ideas. So that's something that we're currently collecting data on. And then we're going to do teacher noticing or teacher video clubs with these videos. But I think that's a great question that you ask. And I think that that's definitely part of the next step to look at differences among student gestures and what that can tell us as educators. Thanks.
Thank you.
I just dropped Golden Meadows link in the chat. She's done a lot of work on gesture, sort of historically, Samantha, if you want to check some more of that out. So, and Janet, thank you so much for being here. This has been really great. I love your analogy of the seed. And I think it's really interesting the way you're talking about it. Sometimes it takes a longer time to germinate, right? Or you're hearkening back to something that you remember from first grade. And we all do that in every subject. Can you talk a little bit more about that, I guess, with mathematics in particular, how you've seen that play out, sort of how you came up with that analogy? Obviously, I'm assuming it was data driven with student interviews, but can you just talk a little bit more about that? Because it's really intriguing to me.
Yeah, sure. I'd be happy to. So to the first question, or the second question, actually, how it came up was when my daughter was little. When I was doing my dissertation when she was born. I was really kind of deep in the work of thinking about how people think. So learning sciences is my background, and I was like kind of being really like Piaget, watching what my daughter did. And she would do these things, and even when she was 6 months, I was thinking, wow, that's kind of algebraic. And but it's not really, like no one would say she's doing algebra, right? So that's when I started thinking, and my colleague had young children too at the time. And we were thinking, well, how do we do this? It's not really pre-algebra, and some people might call it proto-algebra, but that's still more like this idea that it's not quite it, but this is very much the ways of thinking. So that's kind of how we came up with the idea. We thought we must capitalize on what kids are so good at. We a lot of times think of kids as, well, I don't think we do anymore. I don't think any of you do, but think of often before times, people would talk about kids as blank slates. So you kind of have to, we're going to teach them algebra now. But what about taking in all these things that they already do and already think about, and kind of reorganizing them and have them activate them when we think about certain mathematical concepts? And your other question, was it an example of where that would come up? Okay, so so that one example was the clearest one we have. That's the one we've written about, where it was the closing in and in betweenness, and that was the guess. It was guess and check. But the thing that was so great about that guess and check was the student was doing, it wasn't just random numbers, right? The student was like, oh, I'm a little too high, I'm a little too low. So that's where I think they were using their seeds of thinking to really get the right answer. It wasn't random guessing. And in fact, what they did in the full interview is they ended up thinking about covariation, or they ended up thinking, wow, if I cut this number by this much, this number gets cut by this much. So they were starting to think more functionally in that what looked like guess and check. Another example is we've been designing programming experiences for children in DC public schools, where we have them program a little robot, a little Sphero robot that rolls around. And we wanted them to get students to follow a maze with the robot to program it to. But first they had to get the robot to go exactly 1 meter. And we had students, they had distance equals rate times time, or they had to program in a speed and a speed and a time. And they could change the speed and time, and then we'd see how far it rolled. And so the students were trying to do that with the robot until they got exactly 1 meter. So they'd know what those numbers had to be to make it roll exactly 1 meter. And they were trying things, and they were thinking, okay, this is too far for a meter, this is too short. So they were moving the time up and down by tenths of a second to try to get the robot to go exactly 1 meter. So that was again where we saw those two in betweenness and closing in. Going along with that, there's like, is it a little too high? Is it a lot too high? Is it a little too low? That kind of reasoning as well, which seems kind of covariational. So those are a couple examples. I'm just reading. Does that help? And we're coming up with more and more. It's just taking, a lot of interviews and working with children to find more. But I'm sure a lot of us could hypothesize a few, thinking about what students do in algebra classes or calculus classes. Thanks.
I have another question for you too. Since the majority of the people that are on this actually are graduate students and master students, I'm actually the only one who does, I think, in our unit anyway, does research and one-on-one interviews with kids. Can you talk a little bit about some of the challenges that you come up about doing that, and how you incorporate the environment, how you look at other things besides that, the very controlled environment that we just saw. That video is really amazing, right? We can really get into her brain. If you could just talk about your work sort of in general and data collection of that type.
Yes. So we just got done doing a bunch of interviews. These are the bilingual ones. And so there's so many challenges. One being just getting past that interview student dynamic. So a lot of times students, and with a camera there. So there's so many things going on that might be kind of nerve-wracking or throw a student off at first. I think so some of the challenges and how we've dealt with them, the camera being there, students, if you do a longer or enough, maybe a couple interviews, they soon forget the camera's there, so it feels less intrusive. Of course, it's the interviewer and their personality as well, so that you want to be kind of conversational maybe at first. One thing we find to be challenging is the questions and the interview protocol, because we might think of a few questions that we think this is going to be great conversation, and the conversation stops. So tweaking the interview questions has been tricky. There's some interviews where I ask the lemonade question and they say, oh, this one, like some of the people today, oh, this one's more lemony and it's right. And now what? So doing pilot interviews and thinking about the protocol ahead of time and what I might do to follow up has been so helpful and helps us get past those sticking points or those challenges. I think about but it's really just the protocol, the interviewer-student dynamic, and having questions kind of in your back pocket. So a student might take a really long time on a question you don't expect, and then you want to ask some follow-up questions, or vice versa. They might breeze through, and you want to have some extension questions. But yeah, I'd be curious to hear what you're doing with interviews as well.
Yeah, it's tricky. I'm doing work with really young children, 3, 4, 5, and 6-year-olds. And so, a lot of them can't even really use a pencil yet. But, they can, use some manipulatives, but it's an interesting age. Because there's that fine motor skill development that's happening at the same time. And then we're trying to understand some of their, just quantitative understanding. But it uses some of that in-betweenness that you were talking about and connectedness. And it's just a really nice lens, I think, for so many areas, actually. not just
Mhm.
algebraic.
Thanks. Yeah, it's been fun. And and we've been looking at a lot more young children's thinking because we're trying to, that's where we'll see these, that's where we'll see these come up the most. Yeah,
So there's a
thank
question
you.
in the chat.
Let's chat.
Uh-huh.
Yes.
Maybe
Okay.
for her.
So Caroline, yes. And I think that's what we see happen. So whenever a student says something that's incorrect, oftentimes, because it makes sense to them, it's a combination of seeds built unproductively. So how could we address those? I think part of the work is to see what is being applied unproductively, and how can that be addressed. So with the student, the lemonade example, she's employing the seed of adding one to both keeps something balanced. And not correct in that example, but specifically addressing. So when she started to multiply both quantities by something, or both elements by something, and getting the right answer, and then adding something to both elements, that's where you could say, oh yeah, I see that you're adding one to each. Just addressing that specifically. What if you had, 90 and 1? If you added 1 to each, would they still be the same? Just kind of addressing that one piece, that one seed that's being unproductively employed, and then see if you can kind of address that directly and then replace it with something else. Well, here you multiply both by something. Let's see if you do that with 99 and 1, or something like that. So I think it's part of just seeing what these resources are, recognizing that the student isn't just being silly, that they have this thing that they're using, that they make sense to them, and then seeing how it can be redirected, or how something else, that one piece, can be replaced with something else. And also, to answer your question, Caroline, that's still what we're trying to work on now with teachers. Like, what do we actually do? How do we help them use this in the classroom?
Yes, it did. Thank you.
Mm-hmm. Any other questions?
We have just a couple of minutes, so if you've got one you want to throw out.
Well, this has been great. I really appreciate you sharing this. And we share the recording with our grad students who are full-time teachers and can't be here. So I'm sure a lot more people that are not here will get to benefit from this too. So I really appreciate you being part of this. And you actually kicked off our series this fall. So you are number one for fall 2023. So
wonderful. Thank you so much. And I'm always available. You can email here. I'll put my email in the chat. So if people have questions, and I'm happy to share any of the resources, any of the things that we've been writing about this. And and I'd love to hear about things you're doing too that are related. So yeah, if you're ever in DC or Maryland/DC.
Actually, my in-laws live there, so we're there often. I will.
Do they?
Look you
Nice.
up.
Yeah,
Yes.
look me up. Definitely. Because I'm interested in the interviews you do with kids too.
Yeah, it's so fun. Like you said, it's just, I really love that. The excavating. I love that word too. That's what it feels like. You're like, come on.
It is. Yeah. That's what it feels like. I know. Yeah.
So, all right. Well, thank you so much. Thank you, Allison, for leading this too.
Thank you, Janet. It was
You're very welcome.
super interesting. I'm not a mathematician or a math teacher, but I saw a lot of bits that I can incorporate into my science instruction also. So.
And the idea of seeds, these little bitty resources, not algebraic, and it's not specifically to a topic, it was a science thing. So if you look up P-Prims and Andy DeSessa, he's my, down the chain of people who've inspired this. So that's science. It definitely is a thing as well. Okay. Thank you so much.
Thank you.
Bye.
Thank you. Bye.